Today we're going to be talking about reactions of enols and enolates compounds. Okay, so enols are organic compounds that contain a hydroxyl group bonding to a carbon atom having a double bond, and is usually characterized by C double C with an OH bond attached to it. It's enols. Enolates are made of aldehydes and ketones that are electrophiles. So first we're gonna look at enols, and we're gonna make a table for it. So in the table, we're going to have a base, the conjugate acid, the pKa, and then the percent of it that's an enolate. So first, let's look at the NaOH base. The conjugate acid could be water. The pKa would be 15.7. Percent of enolates less than 1%. Then if we look at Na plus attached to an OCH2, CH3, well, we have a conjugate acid of HOCH2, CH3. We get a pK of 16. And the percent of enolate is less than 1% again. But then if we have a base of potassium with an oxygen with carbon, and then we have a parentheses CH3, but 3 of those, and react it with this, we'll get a pKa of 18. And that'll give us around 1 to 10% enolate. But if we were to react it with just NaH, not NaOH, with a conjugate acid of H2, the pKa would be 35. So here is it's a big jump. It's big. And the percent of enolate is actually 100%. But let's say we did lithium with a nitrogen here attached to this, and the conjugate base was this. The pKa is 40, so not too big of a jump between these two, and the percent enolate is also 100%. When classifying these bases, we can say that these two are weak. This is medium. And these are strong, considering they are 100%. Now, if we looked at the enols table. Oh, wait, this is enolates. My bad. This is enols. This time we're going to have a compound here. An example of the compound, and the pKa. Okay, so let's say we started off with an aldehyde. Anyways, an aldehyde. And we had this. We have an H hydrogen here and a hydrogen here. But this hydrogen is an alpha. Our pKa would be 17. If we had a ketone, and we had this, for our example, these hydrogens are both alpha groups. and the pKa is 19.2. If we look at an ester, an example of that would be that this hydrogen would be the alpha with a pKa of 25. What about an amide? NH2. We have the oxygen there, and then this hydrogen would be the alpha. And the pKa would be 30. And we could just keep going. Let's say we had a 1,3 diester compound. An example would be this. Add our oxygens, and then this hydrogen is the alpha. And we can see it's 3 because it's 1, 2, 3, so 1,3 diester. This pKa is about 13.3. Okay, we could keep going. What about a 1,3 dinitrile? Let's see, we have an N here. Wait, this is triple bond C. And then this hydrogen here is the alpha, which will give us a pKa of 11. What about a ketoester? In this example would be this. And this one's a hydrogen alpha. And this is the ester over here. And this is the ketone. And the pKa is 10.7. Now we can look at a quick reaction. What if we had this compound? And we don't know what we'll react it with to give us this. So we can do the mechanism. So first we'll start with our starting material. And let's react it with H3O plus. Okay, so this oxygen's going to attach to this hydrogen. This bond is going to go back to the water to give us this product. Now we need this D in here, so we react it with D2O. This oxygen is going to attach to this hydrogen. This bond is going to go back here, and then this double bond is going to break apart, which is going to give us an OH group and a double bond right there. And if we react that with the wrong color. So the same thing, but we added the hydrogen from the last step. This double bond is going to attach to this, and then this bond's going to go back to the oxygen, and the oxygen has a positive charge. And then this oxygen's lone pairs are going to go back to give us a double bond. To give us our final product with H3O plus in the end. Now we can also look at another reaction, but this one's called racemization. I don't know. Well, we could do it here. Okay, so let's say we started with this product. And we reacted it with an OH group. We'd get this ring. H that. And its resonance structure, where the hydrogen is in the back and the methyl group is in the front. Because this one is the S, this one's also an S, and then this is an R. And the mechanism for this one is we start with the starting material like always. We start with our OH group. This oxygen is going to attach to the hydrogen. This bond is going to go back to that carbon to give us this. That's a negative charge, negative. And then these lone pairs are going to go here, and then this double bond is going to break and go back to the oxygen to give us this, and this is negative charge. Lone pairs on this oxygen are going to go down to make a double bond. And then if we react this product with H2O, this double bond is going to attach to that hydrogen, and then let me just redraw that real quick. And then this bond is going to go back to that OH group to give us this R group, compound. But that's if we react it with water from below the plane. From below the plane, in which would get this R group. But if we reacted it with water, again, but from above the plane, we get this S group. That is the end of reactions with enols and enolates compounds.